ትችላለህ ዶክተር።
Okay. Thank you. ይሰማል አይደል?
አዎ ይሰማል።
Okay. Thank you, Lydia, for organizing this public lecture and also inviting me to talk about galaxy structures and evolution, and also related to my work as well. Thank you, everyone, for being here to learn more about this interesting topic. My name is Dejene Zewdie. I'm a postdoctoral researcher at Northwest University in South Africa, and I'm also current president of Astronomical Society of Ethiopia. So today we'll talk about exploring the galaxies, and also we will learn about the structure and evolution across cosmic time. So as you can see here, like a lot of things. What do you think you are looking here? If I am there in person, it will be good to interact, but I'm talking remotely, so I'll continue by myself. So here, what we can see here, a lot of galaxies, and these galaxies are different types of morphological and also their distance. So we'll go through some of them. So when we talking about the cosmic time or the history of the universe, is always we were starting with talking about the Big Bang. So when the time t is 0, when the universe from like inflating hot and dense states, which is like around 13.8 billion years ago. So that is the beginning of the time and space itself. So from that, the expansions began rapidly with a process, we call it cosmic inflation. So with this cosmic inflation, then there is a combination of, or the beginning of this atom, which means the proton and electron combines to form the hydrogen. We call it a recombination of radiation or cosmic microwave background. After that, after the recombination period, like we call it the dark age. This dark age is we cannot see any kind of star or galaxy, so it's just a neutral hydrogen, or mostly hydrogen gas. So after that, the first star and the first galaxy formed. Can you see my cursor? So here, the first star and the first galaxy is formed.
We cannot see your cursor.
Oh, okay. Let me try to use color. Can you see now?
No.
Okay.
It's okay.
What about now?
Yes.
Okay. So here, the first star and the first galaxy formed with this gravitational collapse of gas clouds. So the first stars is massive and young-lived stars. So at this time, then the beginning of the process of reionization at this stage. So then after that, like the recombination of process, which is the ultraviolet radiation from the first star and the galaxy are ionized the neutral hydrogen throughout the universe. So this process, as I said, we call it the reionization. Then the universe is starting fully ionized, so which is the formation of star is in the universe going to the peak, which is redshift between 2 and 3. So this, we call it a cosmic noon. So then with this process of the peak of star formation, after this, then we will see the older and like the formation of these massive galaxies in the present day. So when we're talking about, in general, when we're talking about galaxy formation and evolution, we have like, in general, we have these 3 questions. What is the physical process driving the formation of the first stars in the galaxies? How do galaxies form and evolve across cosmic time? And what are the role of environment on the galaxy formation, evolution, and as well as aging evolution? So the first question that I want to ask is, what is galaxy? Because when we're talking about all kind of the evolution of the universe, and we want to focus on like observed object, one is the galaxy. So this galaxy is a building block of the universe, and also a massive, is gravitationally bounded system with an different celestial object, including stars, stellar remnants, planets, dust, and gas. At the center, they have this supermassive black hole and also dark matters. So when we study about galaxy, we need to understand what's going on all these stellar objects. So as you can see here, the Milky Way, like a galaxy. So the Milky Way galaxy is our galaxy. So when we're talking about galaxy, we need to understand our Milky Way, because we are living in this galaxy. So this Milky Way galaxy have different structures. So the first one is galactic center and galactic at the center. And then we have also bar structures, spiral arcs, and galactic disk with stellar and dark matter halos. So when you came to when we see our Milky Way from the age-on phase, we will see like this. So as I said, at the center we have this galactic bulge, and also the galactic center here. With this, and the distance of this is around 4 kiloparsec. So this, then in the galactic disk, we have gas and dust. With this, they have star formation going on. That's why we have here O and B stars. So these O and B stars are young and massive stars. So they are blue colors. So if we have gas and dust, there is star formation going on. So when we see here is where we are, the sun is here. So our solar system is at this spot. So from the center is our distance is around 8 kiloparsec. So when we see in general, the size of the Milky Way is around 30 kiloparsecs. So they have galactic halo here, and also this globular cluster, which is a collection of stars. The majority of the stars are old red stars. And here also we have open clusters. The open clusters are the majority. These open clusters are young and massive stars. So when we see the Milky Way in the face-on, we will see like this. So the Milky Way is spiral galaxy. When we say spiral galaxy, what kind of component they have, I'll talk about later. So I already mentioned these are how the Milky Way looks like. So all the components or the structure that I mentioned in the previous slide is the same as here. So the bulge here, and the central bar we have here, and our sun is in the Orion. So like in terms of light year, also you can see like around 26,000 light years. So to understand better, we are classifying galaxies based on different criteria. One is the property of the galaxy, which is we measured parameters, and also depend on the instruments. So for example, here we have like I mentioned here around 4 different classifications. The first one is morphology. Based on their shape of the galaxy, we can classify galaxies into 4 classes: elliptical, lenticular, spiral, and irregular. Based on the nuclear activity of the galaxy, we can classify galaxies again to normal and active galaxy. Based on the star formation, also we can classify galaxies into 3: retired galaxies, star-forming galaxy, and starburst galaxies. I'll talk about those galaxies like classification in details in the next few slides. And also based on the colors, also we can classify into 3: red sequence, blue cloud, and green valley. There are a different classification based on, for example, using infrared observation, we can classify galaxies into different kind of infrared luminosity. So this is not the only way of classifying. There are a lot of classification in galaxy and AGN classification. So when we come to the details about when we're talking about morphological classification, as I mentioned, the shape of these galaxies are, as you can see here, they are different. Elliptical galaxy looks like egg, or they are like at the center they have bright. But when you see here in the spiral, they have different kind of structures. And the irregular galaxy, we didn't see any features, so we cannot say this kind of shape. So we call it irregular galaxies. And also we have lenticular. This lenticular is from spiral galaxy, like involving or transformed to elliptical. So they are losing their arms, or their spirals. Then we can see like this. So we call it this lenticular galaxies. So when we say elliptical galaxies, so as you can see here, they are smooth and elongated shape. So they are spheroid. So when we see, based on the Hubble sequence classification, these galaxies are classified from E0 up to 7. So from spherical to highly elongated. So when, for example, B is the minor axis, A is the major axis. The major axis means when we see like the longest bar, that is the major axis, and the shortest one is the minor axis. So the ratio of this, and when you minus from 1, then when we multiply by 10, we will get the value of n. N is from 0 up to 7. So we have 7 elliptical classification. I'll show you how they are look like in the next slide. So most of these galaxies have no gas and dust. Maybe they have a little bit, so they have low star formation going on there. So most of the stars here are old and red stars. So when we talking about spiral galaxies, they have like at the center they have bulge, some of them, and also they have spiral arm and halo, gas, dust. So they have like enough fuel to form stars. So these galaxies have high star formation going on, especially young blue OV stars. So to classify in better way to understand more about this galaxy. So we can also group into two. So here, as I said, from E0 up to E7, the elliptical galaxies and the lenticular galaxies, sometimes we call it SO galaxies. And we have spiral galaxies we can classify into two based on at the center, if the galaxy have bar, we call it barred galaxies. If there is no bar at the center, we call it normal spiral galaxies. So as I show you, like these kind of features the galaxy have, we call it irregular galaxy. So this the first two galaxies type, we call it these two, we call it early type galaxies, and the next two, these the spirals and irregular galaxies, also we call it late type galaxies. So this classification help us to understand about the galaxy's properties. So that leads us for the color stellar mass diagram. So this, as I mentioned earlier, we can classify galaxies based on their colors. So the color means the difference of two filters. So here we have U minus R colors. So when we see the galaxies are more populated here, we call it these are early type galaxies. So they are more redder. And the galaxies are more populated here, we call it a blue cloud, or they are more late type galaxies. And the galaxies are in this region, these two green line region, we call it green value, which is the transition area from late type or from blue cloud galaxy to moving to the red sequence when they finishing their star formation and the morphological transform to early type galaxies. So the other way of classification of galaxies is based on the nuclear activity. So based on the nuclear activity here, galaxies are classified into two, normal galaxies and active galaxy. When we say normal galaxy, they didn't have supermassive black hole at the center. But when we're talking about active galaxy, the galaxies should have a supermassive black hole at the center. So what does it mean? The galaxy have at the center. So this, we call it in short AGN. So AGN are galaxies which is highly energetic central region. So this region driven by supermassive black hole. So they emit intense radiations across electromagnetic spectrum. So from radio to gamma ray. So then this AGN have different kind of structures. So from the center there is a black hole, and then around the black hole there is accretion disk accreting materials around this black hole. Then next we have this broadline region. This broadline region are strong broad emission. They emit and also they move fast from than the narrow line region. So the narrow line region are further compared with the broad line region. So they have like low motion or slowly motions of gas clouds. And also they have very narrow emission lines we see. So we call it this weaker than. And also we have this jet, this high relativistic jet producing energetic materials or particles. And also we have this obscuring torus, dusty, and they have more obscure dust in this region. So based on this, like as you can see here, they have different kind of components to try to understand this, the AGN. We need to observe in detail. So when we try to observe this AGN, if you are observing from the torus side, we cannot see the inner part of the AGN, like the inner part, the accretion disk and proline region, because of this dusty structure. So we call this type 2 AGN or obscured AGN. If we are observing from the face on, we can see directly to the center of the AGN. We can see clearly the accretion disk and the proline region. So we can say this kind of type 1 AGN, also obscured AGN. So such kind of classification, we call it unifying model. This is the unifying model. So we can classify like AGN in this way. So another way to classify and understand better star forming and AGN using spectroscopic observation. So using spectroscopic observation, we try to classify galaxies into 4. So these are the optical emission lines. So these optical emission lines there are 4: oxygen 3, of H beta, and nitrogen 2 and H alpha. So this optical emission line try to diagnose the galaxies based on the ionization source. So, like for example, if the ionization coming from star formation or region 2, hydrogen 2 regions, this is mostly they have low, the ratio of oxygen 3 H beta is lower because it's coming from young hot stars. But if this oxygen 3 is coming from the AGN is so stronger, and they have like high excitation level. So due to this harder radiation from the supermassive black hole of accretion disk, so we have higher value of the ratio of oxygen 3 and H beta. So when we see here, the green value are star forming galaxies, but here between these two solid line and dash line we have composite, which is the mix of star forming galaxies and AGNs. And the region here, like this one in this area, we call it Cepheid. These are most of type 1 AGN, type 2 AGNs, or type 2 AGNs are here. And here, or we call it Cepheid 2 galaxies. And here are low ionization nuclear emission line region, which is, they are distinguished from the Cepheid by their low oxygen 3 H beta ratio relative to the nitrogen to H alpha. So using this, we can try to understand what type of galaxies we are looking for. So another way, like to searching superluminous quasars or most extreme luminous quasars using mid-infrared observation, which is the WISE infrared survey. This is mid-infrared bands. They have 4 different kind of bands. When we say W1 is 3.4 micron. When we say W2 is 4.6 micron. When we say W3 is 12 micron, and also W4 is 22 micron. So why we are using this, as I said here, when we try to observe galaxies like from the AGN side, we cannot see the inner part. But using this mid-infrared, we can try to penetrate this obscured torus, because at the mid-infrared, the disk re-radiate, and we can see the details about this galaxy. So using the way we classify here is using W1 minus W2 and W2 minus W3, which is here, as you can see here, is the value of the band. So then when we see here, like elliptical galaxies are more populated here, spiral galaxies are also around here, but when we try to see this luminous, obscured, and liners are more populated, or the value of the W3, W2 minus W3 is greater than 4 and above. So using this wide survey, we can study more red and dusty agents and quasars, and also try to search different kind of stars as well. For me, I'm more interested to high redshift quasars. Those quasars are more hot and dust obscured quasars. So I'll talk about how we did such kind of study. So one of the
Dr. Dejene, sorry, I think it will be good if you pause for a question and see if the audience have some question before proceeding to the next slide.
Okay.
Yeah.
There is questions.
ጥያቄ ካላችሁ እስካሁን ፕሬዘንት የተደረገው ላይ
I have a question, if that's okay.
Okay.
Yeah.
Okay, I have two actually. They should be quick. Can you go back one slide, Dejene? I saw one plot that you had. Yes, this one. So a lot of these different galaxies overlap. It seems like you have the liners overlapping with the other kinds of galaxies, like ultraluminous galaxies and all these kind of things. So how do you tell the difference? Like if you have a survey, how can you tell which one is which?
Okay. So if you wait me about this, I have some like more detailed slides. But to answer, like for example, if you are really looking about obscured agent, you try to not only using the wise color selection. So you need to like let me go a little bit and they're all back.
Okay.
So here, the criteria. So for example, I was saying like when we're searching hottest obscured galaxy, the galaxy should be faint or undetected in W1, and they have like a little bit maybe detected in W2. But when they say undetected or fainter, the magnitude should be W1 is greater than 17.
Okay,
But
I understand.
they should be detected in both like W2, W3 and W4, which is they should detect it here. And then we have a criteria called like in W4, we need to be bright. So they should be brighter than 7.7. And also the color cut between W2 and W4 should be greater than 8.2. And also like when you're using W3, you can use the second criteria. So the second criteria is the W3 should be brighter than 10.6 and the color should be greater than 5.2. So then you can see here clearly like where they are populated, right? If I bring for you the previous plot, so you can see here where they are the obscured, the hot quasars. So, but here we have such outliers around here, right?
Yeah.
Can you see my
Yes.
my mic here?
Yes.
Right. So
Yes,
this
okay.
because we are trying to use two different selection criteria. That's why we have a little bit some galaxies are in like here in this region.
Mhm.
Is that clear?
Yes.
Good.
Thank you.
And the second question?
Yeah, this one, I want to ask, why do late type galaxies have no star formation? Because I understand they have a lot of gas. I was working on a paper and I think what we found is more so the dynamics, but are there some other reasons?
So these late type galaxies are like maybe they are in the process of merging, so they have like a lot of gas and dust. So they have enough fuel to form stars.
Mhm.
But when we're talking about early type, they already finished their gas and dust, so they have not enough fuel to form star.
Oh, okay. Okay, that makes sense. Thank you.
Any other question?
So from here, they don't have any further question. Maybe at the end of your presentation, they can ask.
Okay.
You can proceed.
Okay. So yeah, so when you're talking about like how galaxies are formed and evolve across cosmic time, so this is one of the main questions, especially in extragalactic. So AGN, one of the thing is like AGN play a key role for this evolution of by regulating the star formation and also shaping the structure of the galaxy. But how this galaxy is first formed, like, so there are different way of forming. The first one is with the hot halo, with the hot halos, and also there is like a gravitational collapse, and here also in internal process of forming stars internally, which is we call it secular evolution, and also merging two different galaxies. At this time, we will have more like they exchange their gas and they disturb the environment. They form high star formation. Maybe they have like high star formation and then suddenly shut down. We call it starburst. As I said in the earlier classification, we can classify into three. One is the starburst, which is like when the galaxies are having high peak of star formation and immediately shut down the star formation. At that time, we call it starburst. So with these three process, can galaxies are form and transform. So when you're talking about the larger scale structures, the AGN activity is play a key role. So this large scale process triggered by the AGN activity. So as I said earlier, like when we're talking about the evolution of the universe from the recombination period of time and the first galaxy, from the first galaxy, how the galaxies are involved. So when we see this, like the top is redshift, so the redshift is decreasing because when we're talking about the present universe or the present is zero redshift. So this between a redshift 3 and 1 is there is high star formation going on. And why this high star formation going on? So still there are a lot of study going on. And there is here is the massive galaxy are we found in the local universe. So as you can see here is time. So the current or the present universe is around 13.5. So this is time. This is in terms of redshift scale. So as I mentioned, like redshift between 1 up to 3 is the peak of the star formation and density. So these are more related with one is merger of galaxy are highly merging in this, and also the black holes. So when we see the black hole distribution, accretion distribution at this redshift have a similar distribution with the star formation rate, So the AGN play a key role on this physical process that driving the star formation in the galaxy. So the other question that I show you in the beginning of the talk was, what is the role of environment on galaxy and AGN evolution? So when we're talking about environment, between galaxies, maybe we are talking about like protoclusters environment, or maybe we are talking about large scales. So in the cluster environment, so this one of the thing is this rapid gas accretion in the accretion disk. So the AGN activity high, so which is related to galaxy mergers, and also these AGN mergers are going on in this. They have highly obscured AGN are found. So Claudio Ricci in 2017, he studied the details about the growth of supermassive black hole, how to relate it with mergers and also types of AGN. They found that the AGN in the mergers are heavily obscured. So the presence of supermassive black hole at high redshift, at high luminous quasars are very important to understand the formation of clusters and to understand the environment of the supermassive galaxies and supermassive black hole. So this highly high redshift accreting supermassive black hole can provide or give an insight about the formation and the evolution of clusters. And so I want to talk about a little bit about my research interest and the question that we have here, and maybe I'll try to talk about one of the main questions that we studied because of the time, and maybe I'm not going the rest. So the first one is like galaxies are growing, but how some galaxies grow fast, and what kind of growing the mechanisms going on, like they have inside out or outside in, and what makes some of these galaxies assemble their stellar mass within short period of time, like 80% of their stellar mass within short period of time. So, and like how do galaxies are built their stellar mass? So this kind of question we have, how this question came, I'll talk about the next few slides. And also I was working on like to understand this extremely luminous quasars environment. So we are trying to answer, do powerful quasars live in spatial dense environment, or are these luminous quasars are crowded region of the early universe? And also currently I'm working on the cluster environment, like to understand what kind of star formation going on in these clusters. So try to understand what's going on, what kind of star formation history they have. There are quenching or they have high star formation. So I'm trying to understand those interesting questions. If you are interested, we can chat about further. So the first project, what I did is, as
Sorry,
you can see,
Dr. We have one question from the audience.
okay. Go ahead. Let me chat my.
Oh, no. Yeah. I didn't finish. Can you hear her?
Not really.
Okay. So what is it? Yeah. Just give her A second once.
Yeah. Okay. Hi, doctor. Can you hear me?
Yes, I can hear you now.
Okay, so I wanted to ask you, does aging suppress or enhance star formation in their host galaxies?
So aging, there are two processes. One is aging can enhance star formation and also quench star formations. So when this is like the research are going on, like for example, when the AGN are like the outflow are pushing or hitting the gas around this host are like when they try to remove is then the star formation is quenching. But when they accrete and there is no jet or like pushing this or there is no outflow, the AGN is not quenching the star formation. So the star formation like accreting materials and have high star formation going on there. So they have two kind of process. So still we need to understand why such kind of process are going on. So one is there are studies shows, for example, the AGN have this jet, they can like heat the environment and then they quench. But if there is no this kind of outflow, we cannot get such kind of quenching.
Okay, thank you, doctor. So we can say that it's more of both.
Yes, no. So like depend on the like in one galaxy we cannot see both. Just depend on the AGN. So yes, when there are different kind of AGN, but at the same time we cannot see like enhancing and quenching of AGN within one type of AGN. Is that clear now?
Yeah, thank you.
Just give me a second. I want to check my laptop.
Okay. So we have another question here.
Okay.
Yeah.
You can continue.
Yeah.
Okay, can you hear me?
Yes, I can hear you.
I didn't quite get that why and when they lose their spirals, the galaxies. Can you explain that to me, please?
So the galaxies are like, one is the process is when they are galaxies are merging. Let me show you if this is here. Like to show the, okay, no, not here. Okay, so sorry, I was thinking to include like the simulation of these galaxies are merging. Like when the two galaxies are merging, they are like disturb each other, right? So when they disturb each other, they lose their structures. So some of them are getting the gas from the other, but they lose their structure. So at that time, they like they destroy their structures, the spiral arm, and then change it to elliptical, like with through process. It's not with a fraction of time, but it's with long time they lose their structures and then form like going to more lenticular. Then finally when they finish the gas and the dust, they have no a spiral arm. Also, they have no star formation going on. So they completely changed to elliptical galaxies.
Thank you, Doctor. Yeah. You can proceed with the presentation.
Okay. So where we are here, right? So yeah, I was saying is like I was working on the project to try to understand why these galaxies are quickly assembled their stellar mass. And for example, here is Paris 2013. They try to understand galaxy, why they have like different kind of assembly rate. So they use spectroscopic observation from the Khalifa when they try to see the assembly of this stellar mass with different region of the galaxy. So this is they try to see with different region of the galaxy. So when we see here from like this region, these are the galaxies that are showing like almost 2 times the rest of the galaxies. So why this stellar mass galaxy have high assembly rate? That was my question, like why this have like high assembly rate. So when we say assembly rate is 1 over the time of to have 80% of their stellar mass as a function of radius, or as a function of the distance from the center. And when we say relative assembly rate is this assembly rate as a function of R divided by as a function of time. So then what we did is try to use a large sample because they studied with 105, but we have SDSS to study like the statistical study of this mass range. So I took from SDSS and we have like 48,000 sources when we try to see like in color and wise color selection criteria. So above these are another selection criteria to do is these are AGN, these are star forming. This is a wise color selection. And also, as I mentioned, I was trying to see where those galaxies are located in the BPT diagram. So this region are the star forming. As I said, this one is composite and Cepheid and liners. So as you can see here, the red dots are here. We classify those are as AGN, but when we see in the optical emission, some of them are star forming. That's why the classification of AGN, we need to, they are not complete. So we need to, they have contamination. So we need to cross check. So what kind of properties those galaxies they have. But for our understanding is like for our project was that is not the case. We want to like see how many of them are star formation, how many of them are what kind of star formation. So after classification of based on the optical emission lines, we try to understand the star formation history. So the star formation rate here, when we plot based on the BPT classification and also morphological classification, as you can see here is these liners are more low star formation, which is similar with elliptical galaxies. But when we see the Cepheid have bimodal distribution here. So they have, some of the galaxies have low star formation rate, and here is they have high star formation. As we expected, star forming galaxies have high star formation rate. So the star formation rate we expect more are spiral galaxies. We have, like here, as you can see here, they have bimodal distribution of spiral galaxies. But why these spiral galaxies have low star formation rate? So, which is the same as the one of the question that you're asking me is those, like in the transition phase from blue spiral galaxy to red spiral galaxies. So they are like, they look spirals, but they are losing their arms because of the star formation is the gas and dust is not there. So when we try to understand in terms of the star formation and stellar mass, which is, as I mentioned in the beginning, like we can classify galaxies based on the star formation rates. So here we try to see the star forming galaxies are, the majority of them are in the main sequence, which is the main star formation going on here. But when you come to composite, we have some of them are in the main sequence, but the majority also below the main sequence. So they have low star formation rate here. But as we expected for liners are below the main sequence. Here, why we have like the composite in the main sequence? Because composite, as I said, the mix of AGN and star forming galaxies. So the Seyfert also, like they have the main sequence, but the majority also below the main sequence. When you come to the morphological classification of these galaxies, elliptical galaxies have low star formation rate, which is we expected. They have, look here, low star formation rate. And when we see spiral galaxies have the main sequence, but here we have low star formation. So which is similar here, the bimodal distribution, some of the galaxies are here are found in this region, The uncertain are, we couldn't say elliptical or spiral, so we call it this uncertain, which is not classified. So those galaxies are below, like they have low star formation. So, and also here we did the color mass diagram to see where they are located. So they have, the majority of the star forming are in the green valley and also in the blue cloud. But the composite also we have in the red sequence, in the green valley, and also in the blue cloud. So, but when we see liners and elliptical galaxies have a similar kind of position. So these elliptical and liners they have red colors, so they are in the red sequence. But interestingly, spiral galaxies here also we have in the green valley, which is in the transition phase, and they are also in the red sequence because they are losing their features, and but still we can see they are spiral, but they have no their colors is redder. That's why we have here more of so what we conclude from this study is the composite galaxy are and the liners are the majority of our sample. And this, when we see in this, the color, stellar mass, and the star formation main sequence diagram they are more populated in the green value in the main sequence, and also they have the majority also in the red sequence. So in this inside out assembled galaxies are nuclear activities were significantly below the main sequence, and also this could be agent play a key role to quench the star formation and before the morphological transformation. If we have time, I can go for the next, but if you don't have that much time, we can discuss if you have question.
Yes, I think it would be good to stop here since the participants here were here for some longer time. So let us
Okay.
see if we have questions and we can conclude here.
Okay.
Yeah. So,
Uh,
yeah. Okay. They don't have any questions. So can you conclude with
I have a
telling?
question. Can I ask?
okay. Yeah.
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 Okay.
Can take Jason's question. And for us, if you give a conclusion of why study agents and why are they important in astronomy research, and we can conclude with this.
Okay.
Okay.
Yes.
So you mentioned starburst galaxies earlier, and obviously they form a lot of stars very quickly.
Yeah.
What causes them to do that, and then what causes them to stop very quickly instead of just forming stars normally?
So one of the main point there is when they have like merger, when they like the two galaxies, one is star forming, but the other one is not star forming. When they are merging, so they have the high star formation, and because they have the dust and the gas can form with a high peak of star formation rate, and then immediately shut down with a short period of time because they have only that gas, and then they have no like fuel to continue forming star formation. So because of that, they did like they have a lot of star formation in the short period of time. Then immediately they quenching the star formation already. That's why they burst and they have like high star formation with a short period of time.
Okay, thank you. That makes sense.
So yeah, if there is no more questions, so from my point of view, why we are interested to study about AGN, AGN are as you see, they have different kind of components. From that different kind of components, understanding the physics behind that is interesting. For example, why the accretion of the black hole emits like these UV and optical lines, but why absorbed by dust. So we need to understand, and also we need to know the physics behind what's going on, like in the black hole physics. So such kind of questions are curious and interesting. That's why we like astronomers interested to understand better and what is the agent play in the shaping the structure and the influence into the environment. So, for example, let me say this one. In this particular galaxies. So, if you see here is this galaxy is at redshift 4.6, but we try to understand what is the environment look like this, because this is one of the most luminous quasar in the universe. But I was like trying to understand, is there any galaxies around these quasars? Can they like maybe create small protoclusters environment, or these galaxies are living in isolated form, or these galaxies are like involving with different galaxies? So what kind of galaxies are in this region? So that was one of our project is. So because of this supermassive black hole galaxy, they try to create a dense environment. So we need to understand when and where this overdensity started, and what is the AGN role for this kind of environment. That is the main questions we have, in, especially when talking about high redshift AGN.
Okay, and one more question, one final question. If you have any suggestion for undergrad or secondary school students, for them to have the skill or the experience before joining this field, or for those who have interest in joining the field. So generally for astrophysics, and if you have specific advice for those interested in extragalactic astrophysics.
Okay. Jason.
Yes, Dejene. Yes.
I want to change the channel, so I prefer to speak in Amharic.
No problem.
So,
Shukriya.
okay. እንደዛ ከሆነ ሊዲያ አይ ቲንክ በአማርኛ ብመልስ ደስ ምን ችግር የለውም አይደል?
አዎ ፕሪፈር አደርጋለሁ።
ለምን የመጀመሪያው ማለት በደንብ እንድንግባባም ስለፈለኩ ነው። የመጀመሪያው ነገር ምን መሰል ፍላጎታችሁ አስትሮኖሚ ከሆነ ማለት ነው ባገኛችሁት አጋጣሚ አጠገባችሁ ያለው ሰው ስለ አስትሮኖሚ ጥያቄዎችን ሳትፈሩ መጠየቅ የመጀመሪያው ነገር ማለት ነው። ሁለተኛ ስለዛ በቂ የሆነ መረጃ ሰርች ማድረግ። ሶስተኛ ባገኛችሁት አጋጣሚ የሆነ ትንሽዬ ፕሮጀክት ከሰው ጋር ለመስራት መሞከር። እነዚህን ሶስቱን ነገሮች ብታደርጉ ምክንያቱም በአሁኑ ሰዓት ሁሉ ነገር አለ። የዳታ ችግር የለም። የሂውማን ፓወርም አሁን ከበፊቱ አሁን በተሻለ ሁኔታ አለ። ሶ እኔ የምለው ምንድነው በቃ ባገኘችሁት አጋጣሚ ልክ እንደዚህ አይነት ሰመር ስኩል ፐብሊክ ሌክቸር ሲኖር አቴንድ ማድረግ፣ እዛ ላይ ሳይፈሩ ጥያቄዎችን መጠየቅ፣ ፕሮጀክት መስራት የሚቻልበትን ሁኔታዎች ማመቻቸት መፈለግ። እነዚህ ላይ ብታደርጉ የግድ ፐብሊሽ የሚሆን ፕሮጀክት ላይሆን ይችላል፣ ግን ስኪል ዴቨሎፕ የምታደርጉበት እውቀት የምትሰበስቡበት ስለሚሆን ትንንሽ የፕሮጀክቶች ላይ ፓርቲሲፔት ብታደርጉ ጥሩ ነው ብዬ አምናለሁ። ያለኝ ይሄ ነው።
ኦኬ እሺ፣ በጣም እናመሰግናለን ዶክተር ደጀኔ ስለ ጊዜ። እንግዲህ ተሳታፊዎችም ጥሩ ኢንሳይት አግኝተዋል ብዬ ተስፋ አደርጋለሁ። እናመሰግናለን። ቴንክ ዩ ጄሰን ፎር ጆይኒንግ አስ።
በጣም ይቅርታ፣ ምክንያቱም ከ7 ሰዓት ምናምን መኪና ጉዞ በኋላ ነው የደረስኩትና ትንሽ ደክሞኝ ስለነበረ ነው።
አንደርስታንድ እናደርጋለን። እናመሰግናለን።
መልካም ጊዜ። አመሰግናለሁ።
መልካም ጊዜ። እሺ።